Okay, we're back with a continuation of our research methods. So previously, you heard me using the terms population and sample. So population is the entire group that you are applying your findings to. In the migraine study we used as an example, our population would be anyone who suffers from migraines. If we're studying a new treatment for anxiety, then the population is anyone who suffers from an anxiety disorder. The population is not always all humans. It's usually limited by things like gender, age, medical condition, even ethnicity. The sample, then, is the portion of that population that I actually include in the experiment. Now, obviously, I can't try my new medication on everyone who suffers from migraines or everyone with an anxiety disorder, so I gather a sample group. Now, I want to have a sample group that looks like the population I'm studying. If my population is people who suffer from migraines, I cannot include only college students who suffer from migraines. Right? The population has much greater variety than that. My sample must be equally diverse. If I only included men or only women or only people in their 20s in my sample, it would be a biased sample, and I could not generalize my findings to the population at large. There are many different ways of getting your sample. If you're working at a university and you put up flyers around campus, you're going to get what's called a convenience sample. Depending on what you're studying, it's probably also going to be quite biased. You can do what's called a purposive sample. In this case, you pick people that you know represent all the characteristics that you're looking for. Let's say you want to make sure that you include men and women. That must be from certain ethnicities, socioeconomic settings, education level, age ranges. Purposive samples are fine and useful in many situations, but they have limitations in that they eliminate some of the unforeseen variables and the population to which one can generalize. So finally, we have the random sample. In this case, each individual in the population you are studying has an equal chance of being selected for the study. Random samples are preferable in most situations because they reduce the chances of bias occurring. Our next issue is, where are we going to do the research? Are we going to do it in a laboratory of some kind where we can control as many variables as possible? Or are we going to do it in the real world where we cannot control the variables? Laboratory settings are great because we can increase our internal validity by controlling things like room temperature, weather, presence of others, lighting, all the kinds of little factors that can change the results. We are then better able to say that it was indeed our manipulation of the independent variable that led to the change in the dependent variable. So let's take a sleep study as an example. I want to know if lack of sleep affects a high school student's ability to learn new math functions. Now take a minute right now to pause and write down who is the population, what's the independent variable, and what is the dependent variable. Okay, hopefully you said that the population was high school students, the independent variable was the amount of sleep, and the dependent variable was the learning of math. If I do a study in a lab where people come in and actually sleep in the lab, then I can make sure that they are all getting the same amount of sleep I want, that they are not interrupted by traffic noises or car alarms or friends texting them at 2 in the morning. I can then also control the setting in which the learning of math occurs. Right? I don't have to worry about different teachers or classroom setups or other students or whatever. Right? Because I have controlled for all of these things, I can be pretty sure that it was in fact the sleep deprivation that affected math learning and not something else. In other words, my internal validity is high. Now the problem is that by doing all of these things, my external validity actually goes down. I can't say that my findings apply 100% to the real world because the real world doesn't always look like my lab. So if we try to do this study in the real world, we lose control over all those potentially confounding variables. So our internal validity goes down, but we increase external validity. Since I did the study in the real world, well, then it applies to the real world. The goal is to find some balance between these two issues of laboratory setting and internal validity, and then real world setting and external validity. statistics. Now, if you're like me, you just threw up in your mouth a little when I said that word. But it's really not that bad. First, we have two types of statistics, descriptive and inferential. Descriptive, which, surprise, surprise, describes or summarizes data, and inferential that allows us to draw conclusions. So let's look at this data set. Now, apparently, we have here 7 sophomore boys, and we're testing how well they can recall a list of 20 vocab words. Now, 3 of them were so busy looking for their vape that they couldn't pay attention and couldn't remember any of the words. 1 recalled about 10 words, which is actually pretty good. 1 remembered 13, which is great, and 2 cheated. In the data set like this, we can describe the group in terms of mean, right, the average score, median, the middle score, mode, the most commonly occurring. We can also look at things like the range of scores. Now, in this case, 0 to 20, right? And we can look at the standard deviation, which tells us, on average, how far do the scores deviate from the mean. Now, all that information is useful, but it does not allow us to draw any conclusions. It just tells us what the results are. Inferential statistics allow us to draw meaningful conclusions. They tell us things like validity, both external and internal, and statistical significance. In psychology, as in most sciences, we're looking for what's called a p-value that is above my alpha level or confidence level of 0.05. Now, we don't need to get into how one measures this. If you want to know, you should go take an advanced statistics course, and may God have mercy on your soul. What the confidence level tells us is that we are confident that what we observed in the experiment was not due to chance. So if my p-value is above my alpha level, then I am saying that I'm 95% certain that the reason the participants in my experimental group reported less severe migraines was because of the medicine I gave them, and not just because of some other variable. Okay? Doing this allows me to reject my null hypothesis. So a quick note, inferential statistics allows us to reject the null hypothesis. Now, my hypothesis in this experiment is that my new drug will reduce the severity of migraine headaches. The null hypothesis, then, is that the new drug will have no effect on the severity of migraine headaches. We say it this way because it's impossible to prove a negative. Another way of thinking of it is that it's impossible to prove that something doesn't exist. Little green aliens might exist, but no current study has met the confidence level necessary to say they do. But the possibility persists that they might still be out there. Whew. Okay, I need a break.